Okay, this is section 1.2 for pre-calculus. This is part one. We're going to split it up into two sections, or two parts. This is part one. Kind of the introduction to domain, range, functions. Okay, a function is a relation in which every element in the domain is mapped to a unique element in the range. In other words, every x value can only go to one y value, and the domain are all the x's, and the range are all the y's, as you can see right there. Now, when they give you a mapping diagram and they ask you, is this a function? Well, it's very simple. You look at the domain. Okay? If there's only one partner for each domain value, then you're going to have a function. So -1 only has one partner. 0 only has one partner. 1 only has one partner. 2 has a partner. 3 has a partner. So this is a function. Now if I look at the other one, -8 has a partner. -1 has a partner. 0 has a partner. 15 has two partners. See that right there? 15 has two partners. So that means this is not a function. Okay. Next, determining a function when given a formula. They want us to figure out which of those two represents a function. Well, we know what y equals x squared looks like. Okay, y equals x squared, that's a terrible representation of y equals x squared. Okay, we know that y equals x squared is a parabola. Okay, and we know that each x only has one y value. Now, when you switch the variables, okay, y equals x squared looks like that. Okay, x equals 4y squared looks like this. Okay, so that means that there are x coordinates that are going to repeat themselves. Not a function. Now, an easy way to figure it out just by looking at the graph is to use the vertical line test. A graph is a function if and only if no vertical line intersects the graph in more than one point. So as you can see, here's an example of yes, here's an example of no. This one, not sure. Okay, but what about down here? Okay, is this example at the bottom, is that a function? Well, if I pass the vertical line all the way through, it only crosses once. So yes. The second one, well, obviously the x-axis is the y-axis is the telltale here. It goes through the red graph twice. No soup for you. And then the upside down parabola absolutely is. Okay. So basically you're looking at sideways parabolas, circles, ellipses, stuff where a vertical line would pass through the graph more than once. When finding the domain of a function, now we talk about domain, we need to check and make sure no values of x give us 0 in the denominator or a negative, let's be more specific here, or a negative under the square root sign. Okay. For models, we will fit the domain to the situation, okay? And that's going to be called situational domain, okay? Actually, we'll call it relevant. Sorry. I thought it was situational. It's relevant, okay? All right, so they want us to find the domain of each of these. So really what we're trying to do here is figure out what x can't be. All right? Imaginaries don't count. Okay? So we're not worried about negatives or anything like that. We are all about real numbers here. Okay? The domain is all the real numbers. Now in this case, okay, x plus 4 has to be greater than or equal to 0. So you set what's underneath the radical sign equal or to this inequality, subtract 4 to both sides, so x has to be greater than or equal to negative 4. All right, so the square root can be 0 if it's just like it is. If it's on the bottom, that's different. But our interval here, and we're going to write everything in interval notation, we're going to use the bracket because it's an or equal to, negative 4, and then to infinity. So I can use any number greater than negative 4 all the way to infinity. So that would be our domain. Okay. Now, if you have a situation where you have a denominator situation, we do not want 0 in the denominator. Well, what value of x gets us 0 in the denominator? Well, negative 2 does. So every number works. All real numbers work except negative 2 for this problem. So here's how we write that. We're going to write that negative infinity to negative 2. Okay, and again, we always use the parentheses next to the infinity because obviously infinity doesn't have a value, so we can't put a bracket there. We're going to put the parenthesis at negative 2 because we are not counting negative 2 here. Negative 2 does not count. We are not using it. Remember, we called this with the u, we called that a union with negative 2 to infinity. So basically, this is the interval notation for saying all real numbers except negative 2. Okay, so this would be our domain. All right, for the last one, this sort of combines the two. So in other words, what can't x be? Well, x can't be 5 because that makes the denominator 0. And x has to be what? It has to be greater than or equal to 0 because of the square root on top. So now that sort of combines a bunch of things. All right, so we're going to go from negative infinity to 5. Oh, whoops, sorry. Can't go to negative infinity because we have to be a positive number. Okay, so we're going to go from 0 to 5. Now that looks like an ordered pair, but that's an interval notation. All the real numbers from 0 to 5. And then we're going to combine that union with 5 to infinity. Because the parentheses here take care of this. The greater than or equal to 0 part is taken care of. The infinity takes care of that. Okay, so that would be the domain for that. Okay. Now, when it says determine the range, okay, when it says determine the range, y equals 2x is a line. Think about this for a second. There is no restriction on x. You can plug any x in and get a real number y out of that equation. So when that happens, that's all real numbers. Well, all real numbers you'd write as negative infinity to infinity. Notice we're doing all notation here, all interval notation. Okay, so you got to know how to do interval notation. For part B, y equals x squared. Okay, so we know basically that's the basic drawing of it. Okay, well, there's no restriction on x, but if you notice it's x squared. So no matter what I plug in for x, y is always going to be positive. So our interval is from 0 to infinity, because all these y values of all those points are going to be 0 or bigger. Okay? So we only use the positive numbers in that situation. Now, C. Okay? C. 2 over x. Now, if you plotted that in your calculator, it would look something like this. Okay? Now, x can be any number it wants to be, except 0. Okay? X can't be 0 because 2 divided by 0 is undefined. Okay? But what happens here is, since x can't be 0, that means y can't be 0 either. Matter of fact, y is never going to be 0, because 2 divided by any number will never ever be 0. You'll get a non-zero number. So your range is negative infinity to 0, union with 0 to infinity. Again, all real numbers except 0 for the range. Last one here. We have an upside down parabola. Okay? The point here is very critical. The y coordinate is 4. Now you notice it's upside down, so we're looking at all the y values now are going to be less than 4. Now it goes on forever and ever and ever, so negative infinity to 4 is our range. Because you always start small and then go up to the highest value. That's the range. Now, one of the most important properties of functions that model real-world behavior is they are continuous. Okay. If a graph does not come apart, it is continuous. Okay? Now let's talk about a couple things here. First, you notice this graph. It never stops. I put my stylus down and I'm drawing the curve and I never have to pick it up. Okay? This is an example of a continuous graph at all x values. Okay? Now, what happens if there's a hole? Okay, what happens if there's a hole? Well, that means that when I drew my graph, I got to a hole. I had to stop, pick up my stylus, and then keep going. Now, you might say, well, Mr. Habit, there's a point up there that fills in for that. And that's fine. But anytime I have to pick up my stylus or my pencil, that means that I have a discontinuity. Okay? And it is a removable discontinuity because I have this point up here. Somewhere in that function, there is a value for a. Somewhere. All right? And we'll do specific examples as to how to figure that out in class. But that is an example of a removable discontinuity. Now, a jump discontinuity. A jump discontinuity is not removable. Okay? Here's why. So here's my graph, and I get up to the hole. A would be the x coordinate of this point, of the hole. Now here's what happens. Not only do I have a value up here, see, I jump to this point. Now you might say, well, Mr. Habit, I jumped to this point from up here. I jumped up there. Well, the difference is it was just a single point. Here, I'm jumping, and then my function continues from that point. So the entire function jumps from the hole to the closed-in point. And then the function continues. Okay, so that's the difference. That's called a jump discontinuity. Jump, also a great song by Van Halen for all you rock and roll fans out there. And it is not removable. It is not removable because the entire function is jumping up and continuing. It's not just a single point. Now, an infinite discontinuity, infinite means that basically it's an asymptote. And we talked about asymptotes a little bit last year, and we're going to kind of get into it more in the next video. But if you have an asymptote, like this would be a vertical asymptote, x equals a would be a vertical asymptote. Okay? That means that the graph jumps, or not jumps, but there's no hole. Okay? That just means that no matter what a you plug in, you're never gonna get a value for it. Okay? So something like 1 over x would be an infinite discontinuity. Because at 0, you're never going to get a value for y. You're not going to get a defined value. Okay? So that would be an example of an infinite discontinuity. Be an asymptote. Okay, that's it for the first part of 1.2. Make sure those notes get filled out. We will definitely go over some problems in class. You'll have an opportunity to work on those. And we will get into part 2 video tomorrow.